Hi, today I'm going to be talking about Turing machines. So let's get started. So a Turing machine is, in short, a mathematical model of computation that defines an abstract machine in which you manipulate symbols on a strip of tape according to a table of rules. So this is it has a very simple approach to the model that has been made, but it is capable of simulating algorithms that are very complex. So the way it works is that it operates on an infinite memory tape and it's divided into small cells. So the machine positions its head over a cell and reads or scans the symbol there. Then, as per the symbol and the machine's own present state in a finite table of user specified instructions, the machine then writes a symbol in the cell, either moves the tape one cell left or one cell right, and then, as determined by the observed symbol and the machine's own state in the table, either it proceeds to a subsequent instruction or it halts the computation. So this is a simple and explanation of how the Turing machine is works like an outline. Uh, to further understand this, let's look at what a generalized class of context-free languages are. So we know that there are the regular languages. They come under a broader classification of languages known as context-free languages, which in turn come under a broader classification of languages called recursive languages, and so on and so forth. This increases up to the point where you have non-recursively enumerable languages, which are like the superset of all the other languages that are present. So this should make it clear. And Turing machines are generally designed to handle context-free languages. And yeah, so all these languages that we talked about. So when we start from top to bottom, we read it as recursively enumerable languages are known as type 0 languages, and context sensitive languages are known as type 1, and context free are known as type 2, and regular languages are known as type 3 languages. So instead of using these terms, one can replace each of these terms with type 0, type 1, type 2, type 3, and so on. Moving on. So Turing machines model the computing capability of a general purpose computer, which you can informally describe as some an effective procedure that is finitely describable, and it is well defined, and it has a discrete way of carrying out its steps. It has a discrete way of carrying out steps that are predefined and are mechanical, and it always you can be sure that it will always terminate a computable function. And yeah, the last point is a function computable by an effective procedure. Turing machines formalize the above notion. Yes, that's about it. And so yeah, one of the most important things one you should learn about when you read about the Turing machines is the Church Turing thesis. So you can in the this thesis in short is that if you have an that that there is an effective procedure for solving a problem if and only if there is a Turing machine that halts for all inputs and solves the problem. Now this is one way of looking at whether or not a problem is solvable or not. So this thesis here says that only if you have a Turing machine that halts for all the inputs and solves all the problems, only then you can say that there is an effective procedure for solving the problem. Uh, so yeah, this according to this thesis, there is no other powerful machine as compared to the Turing machine. So yeah, also DFAs and PDAs do not model all effective procedures or computable functions, but only a subset. Like I mentioned in this slide earlier, uh, DFAs and PDAs are used to solve the subset of the languages that are mentioned here when compared to Turing machines. Um, so deterministic Turing machine is it's a two-way infinite tape. It's broken into cells, and each cell will contain one symbol each, and so there is a two-way read and a write tape head. So an input string is first placed on the tape. It is padded to the left and right infinitely with blanks. Read write head is positioned at the left and at the end of the input string. So then there is also finite control that is mentioned, this part shown here. It is a program that contains the position of the read head, that is the current symbol that is being scanned at the moment, the current state. So in one move, depending on the current state and the current symbol being scanned, the Turing machine, it either changes states or it prints a symbol over the cell being scanned, and it moves its tape one cell left or one cell right. So yeah, there are many modifications possible, but the 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 thesis that we've read here, Church-Turing thesis, it says that all these modifications, there is an equivalence to it, which this thesis declares. Moving on to so this is one example worth looking at. So the question here is, the example here is as shown. So 0 to 1 star and W ends with 0. So this is what the conditions given. So if you start formulating the the Q, sigma, F, and deltas present in this is what it looks like. And once you formulate the table, this is what it looks like. So yeah, and this table, I mean, yeah, we know that this is the table with the symbols and the states. So we know that Q naught is the initial state, and it's also known as the scan state. And Q1 is the verify O state, and Q2 is the final state, because there is no other state after this. And so when we move on to this, so yeah, proceeding further with this question, the yes, so proceeding further and expanding this question to a slightly different question, there is O to the power n and 1 to the power n. O is 0 to the power n and 1 to the power n. So this basically says that how many O's or 1's there can be in a sentence, in a word, part of that is part of the language. So yep, this is the table again with symbols and the states, and this is a set of words that can be formed. And also there is in this sample computation, there is a presumption that the Q state looks rightward. So yeah, we did mention that when we were looking at the working of the machine. So yeah, and when we try to make it, so each of those problems, how will the Turing machine solve? So this example, when we read it, we can see that, let's say we try n is equal to 2 or 3 first, and then we say Q naught is on 0, and then it replaces with the character to x, changes to Q1, moves right. Q1 sees next 0, ignores both zeros and x, and keeps moving right. Q1 hits a 1, replaces it with y, state to Q, moves left. Q2 sees a y or a 0, ignores, continues left. When Q2 sees x, moves right, it returns to Q0 for looping step 1, which was Q1 is on 0 and This was step one, and it goes to step one through 5. So when it is finished, Q0 sees Y, and there are no more zeros. It changes to the pre-final state Q3, the state before the final state. Q3 scans over all Ys to ensure that there is no extra, and at the end, to crash on seeing any 0 or 1. When Q3 sees B, all zeros matched, 1 0 is done, changes to final Q4, and then at the end there's a blank line for final state Q4. So yeah, one of the things to keep note in this machine is that it has the ability to remember what it's done and stored before. Otherwise, no, most of these things wouldn't be possible. Um, yeah, which is probably one of the things that helps the Turing machine to be so powerful. Yep, and so I hope this example and the explanation should be clear to make understand how the Turing machine works. Thank you.